Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, I'm going to discuss about different types of polarization. Under the head electric and magnetic materials, we have already seen the introduction to dielectrics, and today we are discussing the types of polarization. So let us see the brief outline of how we are going to discuss about this topic. First, we'll see the definition for polarization and then see different types. So, the first one is electronic polarization, ionic polarization, orientation or dipolar polarization, and space charge polarization. So, we are going to see the definition, the phenomena, and derive expressions for all these different types of polarization. Now coming to the definition of polarization, the process of producing electric dipoles inside the dielectric by the application of an external electric field is called polarization. So it is the process of producing electric dipoles. How they are produced? By the application of external electric field. Now let us see the diagram. So here we are seeing in the first part of this diagram, the first part what we are seeing is non-polar molecules, where these molecules are non-polar, means the positive and the negative are coinciding with each other. The center of gravity of the positive charge and the negative charge, they are coinciding with each other. This is without the application of electric field. So, when an external electric field is applied, here as you see in the second diagram, E is not equal to 0, means we have applied some electric field. Then what is happening to this is electric dipoles are produced, means you can see the separation of the charges, plus and minus. This is how they are separated. So, what are electric dipoles? Electric dipoles are nothing but two equal and opposite charges. If I say this is plus Q and this is minus Q, they are separated by a distance R. So, this forms an electric dipole. They are equal in magnitude but opposite in charge. So, this is positive, this is negative. But when it comes to the magnitude, both are having the charge Q. So, that is how electric dipoles are formed in the presence of an external electric field. And this process of producing the dipoles due to the electric field, we are calling it as polarization. So, I think the definition should be very clear before we discuss about different types of polarization. Now, what are the different types of polarization? The first one is electronic polarization, then ionic, orientation or dipolar polarization, and space charge polarization. So, we will discuss one by one different types of polarization. So, what is the first one we are going to discuss is electronic polarization. What is electronic polarization? So, when an electric field is applied on a dielectric material, then all the positive nuclei of the atoms move in the field direction. And all the negative electron call out will move in the opposite direction. This is what is happening in electronic polarization. So, now let us see the figure here. We are discussing about the electronic polarization. So, when there is no electric field that is applied, that means E is equal to 0. What is happening here is the positive and the negative charges, they are coinciding with each other, and so there is no net dipole moment. But as we apply the external field, when we are applying the external field, that means E here is not equal to 0. The electric field is not equal to 0 means we have applied some electric field. then what is happening? The positive charges and the negative charges are being aligned. They are aligned in opposite direction. So the positive nuclei move in the field direction and the negative electron cloud move in the opposite direction. So all the positive charges are moving towards the negative plate of the or negative side of the electric field, and the negative will move on to the positive. So dipoles are formed and they produce dipole moment. So when we see a situation like this where the positive and the negative charges, they are separated by a distance, we see there are dipoles. And whenever there are dipoles separated by a distance, they constitute dipole moment. So what is happening here is the electron cloud readily shifts towards the positive end of the field. So I already told you this point. When I am talking about this negative field, this is on to the positive side of the electric field and this is on the negative side. So the extent of this shift by the electrons depends upon the field strength. Means the applied electric field. If the amount of electric field or the intensity of the electric field applied is more, the shift is also more. So what we say is they are proportional. So the extent of the shift is proportional to the applied electric field. And the dipole moment is given by the product of the charge and the shift in the distance. Suppose we are talking about the charges, two charges equal and opposite in charge, plus q and minus q. They are separated by a distance r. Now if we have to write the dipole moment, which is denoted by mu, mu is equal to charge multiplied by the distance of separation between the two charges. So the dipole moment is the product of charge and the shift distance, or the distance between these two charges, how much they have shifted. You may sometimes denote the shift by x or denote the distance by r, whatever the representation may be. It is always the product of the charge and the shift in the distance. Now let us derive the expression for electronic polarization. So we have seen what is electronic polarization. Now we are going to derive the expression for electronic polarization. So what we are considering here is, let the displacement between the centers of the nucleus and the electron cloud be x. So what we have to consider here, if I am considering the center of the nucleus to be positive charge and the electron cloud as negative charge. So here this is not positive charge and negative charge. So this is all about the center of gravity of the nucleus, and this is the electron cloud, and they are separated by a distance x. Now, what is the charge on the nucleus? The charge on the nucleus is given by Ze. Z always here represents the atomic number. Z is the atomic number. So when we are telling about nucleus, it is the number of protons that contribute to the charge of the nucleus. So they are positive, and also it depends upon the number of protons that are there, which is dependent on the atomic number. So what we are considering here is, let Ze be the charge of the nucleus. Now when this is Ze, we know the atom as a whole is neutral. So the charge on the electron cloud will be minus Ze, equal in magnitude but opposite in direction. We are talking about the electron cloud, so we are considering it as minus Ze. And this electron cloud is enclosed in a sphere of radius r. Now the charge density due to the negative electron cloud of radius r means I am considering this negative electron cloud like this, whose radius is capital R. And this is all we are talking about. There is no external electric field. Now we are going to write the expression for charge density. What is charge density? It is the charge per unit volume we are talking about the charge density of the negative electron cloud. So whenever we say density, density is mass per unit volume. So whenever we are talking about charge density, it will be the charge per unit volume. So what we have considered here, the charge is the net charge of the electronic cloud is minus ZE divided by volume. We have considered a sphere. We have considered a sphere of radius capital R. So what is the volume of the sphere given by 4/3 pi r cube. So rho is equal to, rho here represents what? Charge density. So the charge density rho is given by charge per unit volume. Charge given by minus ZE. This is for the electron cloud. And 4/3 pi r cube is the volume of the sphere. So I can rearrange the terms and write it as rho is equal to minus 3/4. I'm taking 3 to the numerator. So it is minus 3/4 ZE by pi r cube. So this is equation 1. We'll be using it later. So what is rho? Minus 3/4 ZE upon pi r cube. Now, the Lorentz force which tends to separate the positive nucleus from the negative electron cloud. So we are talking about the Lorentz force that acts between these two charges and tends to separate them, the positive nucleus and the negative nucleus, is minus ZE into E, because we know whenever we have E, the electric field applied, E is equal to F upon Q. The electric field is given by the force, that is the Lorentz force, divided by the charge. So I can write F as E into Q. E is the applied field and Q is the charge. So here what we are taking the charge for the electron cloud as minus ZE, and the electric field that is applied is E. So the Lorentz force is given by minus ZE into E. We have taken this as equation 2, which will again equate it later. Then next comes the Coulomb force. The Coulomb force of attraction or repulsion. If there are two opposite charges, it will be the force of attraction, and if there are similar charges, it will be the force of repulsion. So whenever we are talking about a Coulomb force, the Coulomb force is always directly proportional to the product of the charges and inversely proportional to the square of the distance. So we can write the formula for Coulomb force as F is equal to 1/4 pi epsilon naught into Q1 Q2 by R square. So this is the general formula for the Coulomb force. So it is directly proportional to the product of the charges and inversely proportional to the square of the distance. So now how do we write the expression here? So now we are writing the Coulomb force between the positively charged nucleus and the electron cloud. What will be the force of attraction between the two? So that will be given by the product of the charges Q1 and Q2. Q1 I have taken as plus ZE due to the nucleus. And then what is the charge enclosed in the sphere of radius x? We have considered an electron cloud of radius x here. So we are taking this as 4 pi epsilon naught x square. So we can also write it as 1/4 pi epsilon naught into ZE into charge due to the electron cloud in a sphere of radius r. So this is the charge due to the electron cloud upon x square, because we have considered the distance between these two as x square. So this gives us the Coulomb force. So now we will find out what is the charge that is enclosed in the sphere of radius x. So what will be the charge enclosed in the sphere? It will be 4/3 pi r cube rho. Rho here is the charge density. So this is the charge per unit volume. Now we want it in a volume of 4/3 pi x cube, because we have taken a sphere of radius x. So how do we get the total charge enclosed by the sphere? It will be 4/3 pi x cube into rho. So we have already got the formula for rho from equation 1. So what is rho equal to? We got it is minus 3/4 Z upon pi r cube. So we are going to substitute that here for. So 4/3 pi x cube minus 3/4 into Z by pi r cube. So we can simplify this now. So how do we simplify? Pi and pi will get cancelled. 3 and 3, 4 and 4 will get cancelled. So what is there in the numerator? We have minus Z into x cube, and in the denominator we have r cube. So the charge enclosed by the sphere of radius x, this is the charge enclosed by the sphere of radius x is minus Z into x cube by r cube, and we have taken this as equation 4. Now we are going to substitute 4 in 3 because we want the Coulomb force. What is Coulomb force? Q1 into Q2 by 4 pi epsilon naught x square. So Q1 is Z. And what is the charge enclosed by the sphere we got now? As minus Z into x cube by r cube. We are going to simplify this. What we have in the numerator is Z into minus Z into x cube upon 4 pi epsilon naught x square into r cube. So minus Z into minus Z, we'll have minus Z square E square. X square and x cube, they get cancelled and we have one x in the numerator upon 4 pi epsilon naught r cube. So this is the Coulomb force we are getting, minus Z square E square into x by 4 pi epsilon naught r cube gives us the Coulomb force. Now we are going to compare equations 5 and 2. So what are the equations 5 and 2? In equation 2 we have written the Lorentz force, and in 5 we have written the Coulomb force, because in equilibrium position the Coulomb and the Lorentz forces will be equal. So we are going to equate these two equations 5 and 2. So what is 5? Minus Z square E square x by 4 pi epsilon naught r cube, and this should be equal to the Lorentz force Q into Q. So minus Z into E. So now from this equation I have to write the displacement. So how do we write? Minus Z square E square x upon 4 pi epsilon naught r cube is equal to minus ZE into E. What I want to get? I want to find the displacement, electron cloud displacement. So I'll just transpose the terms. So x will be equal to minus ZE into E divided by minus Z square E square into 4 pi epsilon naught r cube. So ZE and one ZE will get cancelled. So what we have in the numerator here is x is equal to 4 pi epsilon naught r cube upon z. Minus and minus also will get cancelled. We have numerator and denominator minus. So this multiplied by e. So what we are getting here in equation 6, 4 pi epsilon naught r cube upon ze. Sorry, there is a e also here. Ze into e. So this is equation 6. Now the two charges plus Ze of nucleus and the minus Ze of the electron cloud, they are displaced through a distance x. Now we have to write the electric dipole moment. And we know the basic formula for dipole moment we have seen. Mu is given by, we are writing here as mu e because it is due to the electronic polarization. The dipole moment due to electronic polarization is charge multiplied by distance. What is the charge? Ze. What is the displacement? X. So we have already calculated what the displacement x is, 4 pi epsilon naught r cube by Ze into E. So here Ze and Ze will get cancelled. So we are left with mu E is equal to 4 pi epsilon naught r cube into E. This is equation 7. So what we have got is the dipole moment, which is nothing but the product of the charge and the separation between the charges or the displacement. Now we are going to write the expression for electronic polarizability. Electronic polarizability is denoted by alpha E. Alpha generally represents the polarizability and E, suffix E represents due to electronic polarization. So it is the dipole electric moment upon electric field. So what is the net dipole electric moment? We got 4 pi epsilon naught r cube into E by the electric field is E. So E and E will get cancelled and you have alpha E is equal to 4 pi epsilon naught r cube. So this is what we have for electronic polarizability. So the electronic polarizability alpha E is given by 4 pi epsilon naught r cube. This is one part due to electronic polarization. What capital R represents here is the radius of the atom, because epsilon naught is a constant, 4 pi is a constant. So alpha E depends upon the radius of the atom. The next one is ionic polarization. We are going to discuss about ionic polarization. So what is ionic polarization? It takes place in ionic dielectrics due to the displacement of positive and negative ions under the influence of external electric field. So what is the difference between the two? You need to understand here. It is the displacement of positive and negative ions under the influence of external electric field. So what happens when an electric field is applied on an ionic dielectric? The positive ions move in the field direction and the negative ions move in the opposite direction. So when these positive and negative ions are being separated, they are moving in opposite direction, dipoles will be formed. We are getting dipoles. And so this phenomenon we are calling it as ionic polarization. So ionic polarization is nothing but the separation of positive and negative ions in the presence of an external electric field. So let us now derive the expression for ionic polarizability also. Just like we have derived expression for electronic polarizability, we'll be deriving the expression for ionic polarizability also. So now let E be the charge of the ions and capital M and small m be the masses of the negative and positive ions. For the negative ions we have taken plus m and for the positive ions we have taken small m, whatever, either way. Now when an electric field is applied on an ionic dielectric, we have taken a dielectric and then we have applied an electric field. Then what happens? The positive ions displaces in the field through a distance x1 and the negative ions get displaced through a distance x2 in the opposite direction. So what is happening here? The ions are getting displaced. If the positive ions are shifting on to the negative side of the electric field through a distance x1, so the negative ions will be displacing through a distance x2. So let us see the figure. If you see the figure here, we have taken for example NaCl. NaCl here I have Na positive and Cl minus. So these are two ions that are formed. Whenever we are talking about ions, I can write NaCl as an ionization. They form Na plus plus Cl minus ions. So the positive ions and the negative ions. So when a field is applied, if we are applying a field, then what we are talking about is, this is the chlorine ion which is negative, whose mass we are denoting by capital M, and this is the positive ion Na plus, whose mass is denoted by small m. Positive ion, mass small m, negative ion, mass capital M. We have taken the example for NaCl. Now, this is displaced through a distance x1 and this is displaced through a distance x2. This is due to the external electric field. So, what will be the dipole moment? So, again, the formula we have for dipole moment is charge multiplied by the displacement. What is the charge we have taken here is E. E is the charge and the displacement between the two ions will be, now this is x1 and this is x2. So the total distance will be x1 plus x2. The total distance between the two ions after separation due to electric field we have to consider. So mu is equal to E. I am taking the mod of E I have represented because we are just taking the magnitude and we are not considering the charge. So into x1 plus x2, this gives us equation 1. Now, what we have here is against the displacement of positive and negative ions, restoring force acts and opposes the displacements of cations and anions, the positive and negative ions. There is a force which we call it as the restoring force. And under equilibrium conditions, the restoring force F is proportional to X. So, more the displacement, more the restoring force. Or we can write the general formula as F is equal to Kx. So, F is equal to Kx. K is the elastic constant we say here. X is the displacement and F is the force. Now, we are going to write for the negative ion and the positive ion what are the forces. So, F is equal to K1x1 for the negative ion because we have taken it is displaced by a distance x1 and the constant here is K1 and F is equal to K2x2 for the positive one. So, we can write x1 is equal to F upon K1 because F is equal to K1x1. I want to write what is x1 equal to. So, it is F upon K1. Now, F is equal to K2 x2, so we want to write x2. So, x2 is equal to F upon K2. Now, we are going to write what is K1. K1 here is the force constant I said or the elastic constant which is given by m omega naught square. So, m omega naught square here, m represents the mass of the negative ion and omega naught represents the angular frequency. So, K1 here is capital M omega naught square and K2 is small m, the mass of the positive charge, omega naught square, where omega naught is the angular velocity of the ions. So, how do we write x1 now? X1 is F upon K1. So, F upon capital M omega naught square and x2 is equal to capital F upon small m omega naught square. So, x1 and x2 we have got. Now, we know that F is equal to E. So, because we have x1 is equal to F upon K1 and x2 is equal to F upon K2, we know F is equal to E into E and K1 is capital M omega naught square and K2 is small m omega naught square. So, what we are writing here, x1 is equal to E upon, I'll write for F as E into E. Small e is the charge, capital E is the electric field applied. So, x2 is equal to E by m omega naught square. So, this gives us equation 4. So, now we are going to substitute this equation 4 in equation 1. What is our equation 1? Mu is equal to E into x1 plus x2. This is the dipole moment is the charge multiplied by the separation between the two ions given by x1 and x2. So, we are going to substitute the values of x1 and x2 from equation 4. So, mu is equal to E into small e into capital E by m omega naught square, capital M for the negative ion and small m for the positive ion. So, I can take out EE and EE are common and omega naught square is also common. We can take out from this equation, I can take out E into EE, and omega naught square also I can take out from the bracket. So what is left here is 1 by m, and what is left here is 1 by small m. So I can write it as small e into small e is E square. So I'll write it as mu is equal to E square E by omega naught square into 1 by capital M plus 1 by small m. So this is what? Mu, the dipole moment. Now, how do we get the ionic polarizability? So our main aim is to find the polarizability due to this ionization. So alpha I here represents the polarization due to ionic separation. So alpha I will be the dipole moment upon electric field. Dipole moment denoted by mu, electric field denoted by E. So what is the dipole moment we got? E square into E by omega naught square upon 1 by capital M plus 1 by small m. This is from equation 5 we got. Whatever we got in equation 5, we are substituting here for mu upon capital E. So this capital E and this capital E will get cancelled. So what is left here is E square by omega naught into 1 by capital M plus 1 by small m. This is alpha I. So all the terms are clear. E here represents the charge. Omega naught represents the angular velocity, or you call it as angular frequency. When I say omega naught, it will be the natural frequency. And capital M here is mass of negative ion. And small m represents the mass of positive. So this is the expression. I'll take this is capital 2 due to ionic polarization. Now the third one is oriental polarization. What is oriental polarization? So when an electric field is applied on a polar dielectric, then all the dipoles tend to rotate or orient, we call. That is why we are getting the name oriental polarization. They tend to rotate or orient in the field direction. So what is a polar dielectric? A polar dielectric is a dielectric in which there is separation of charges. Already there are different dipoles, but the dipoles are arranged in a random fashion. So what happens here is the dipole moment increases gradually. And this phenomenon we are calling it as oriental polarization. So oriental polarization is due to orientation of the dipoles of a polar dielectric due to electric field. So this takes place only in polar dielectrics. So first we need to understand what are polar dielectrics. Now if you see here, this is negative, positive, means already they are separated. So wherever these charges are separated by a small distance, then we call them as polar dipoles or polar dielectrics. So in the absence of an electric field where E is equal to 0, what do we observe here? These dipoles are oriented in random fashion, random manner. See, positive, negative here, negative is this side, positive. So there is no particular direction for negative and positive. They are in a random fashion. Random means in any direction they lie. So what happens to the net dipole moment is 0. They cancel out and the net dipole moment is 0. But when we are applying an electric field, we have applied an electric field like this. So I say this is positive and this is negative. Electric field, what is happening? All the negative are oriented towards the positive and all the positive are oriented towards the negative. You see, these are all positive. So this is what we are talking about orientation. You can see from the figure and understand this is the random arrangement of the dipoles in a polar dielectric, and after the application of an electric field, means E is not equal to 0 here, then they are getting oriented in the opposite direction. Now we are going to derive the expression for polar, dipolar polarizability or orientational polarizability. So what is the formula? It is the total dipole moment to the total number of dipoles. So mu, average dipole moment, is given by mu is equal to total dipole moment due to all the dipoles divided by the total number of dipoles. So how we are going to derive is according to the statistical mechanics. Why we follow statistical mechanics? Because there are large number of dipoles. When you are talking about an Avogadro number, it is 6.023 into 10 to the power of 23 molecules. So we have to consider the dipole moment of all the molecules. So the average component, we are talking about the component of the dipole moment, is given by mu cos theta. And this is the expression we have. You can take it as it is, not derive. So mu cos theta is equal to integral. Theta is equal to 0 to pi. Theta ranging from 0 to pi. Mu cos theta. Sin theta d theta into e power mu e cos theta by kbt. Upon integral 0 to pi sin theta d theta into e power mu e cos theta by kbt. So we'll take this as equation 2. Now what we have to do, we'll have to solve this integral. So in order to solve the integral, we'll make certain assumptions and solve them. So to evaluate the integral, we are considering let mu e by kbt be equal to a. So when mu e by kbt is equal to a, mu e kbt cos theta is equal to x. So when we are taking this and mu e by kbt is equal to a, I can simply write a cos theta is equal to x, because this is a. So I can write this is a cos theta is equal to x. Now if I differentiate this, what do I get? Differentiating cos theta, I get minus sin theta. So minus a sin theta d theta is equal to dx. Now we are going to substitute this in equation 2. So in equation 2, what we have? Mu cos theta is equal to mu integral minus a to plus a. So the limits which are there from 0 to pi will now, on this substitution, they are going to go from minus a to plus a. These are the limits. So minus a to plus a, x upon a into minus dx by a, because we have a sin theta. So here minus dx by a into e power x. What is x here? X is a cos theta. A cos theta is mu e by kbt into cos theta. So we have substituted everything in the equation 2. So now we are going to just simplify. So we can write the form, because it is of the form x into e power x dx by e power x dx. We can simply write it as e power a plus e power minus a by e power a plus e power minus a minus 1 by a upon substituting the limits. And we consider it, let it be equal to L of a. So what is L of a? We call it as a Langevin function. So what is cos theta now equal to? L of a, the Langevin function. This is the result. So cos theta is equal to L of a. This is the equation 3 we have taken. Now what will be mu cos theta? Mu into L of a. Now what we are going to do is, we are going to plot a graph taking the value of a along the x-axis and the Langevin function L of a along the y-axis. Okay, mu e by kbt, that is a is equal to 1. Now from the graph, what is clear? For large values of a, that is for very high field strength, the function reaches the saturation value unity. So now as the value of a increases, for higher values of a, what is happening? It is increasing and gradually becoming constant. And what is this constant equal to? It is equal to unity. This is one important result we are getting from the graph. Then this saturation corresponds to complete alignment of dipoles in the field direction. So whenever we are applying an external field, all the dipoles that are oriented in random directions, all of them will complete their orientations in the direction of the field. So that cos theta is equal to 1. So if cos theta is equal to 1, then we have mu cos theta is equal to mu. Now let us see different cases. The first case. What is the first case? When the field strength is not too high and the temperature is not too low. Under this condition, A is much less than 1. What is A? We have considered, let mu E by kBT is equal to A. So mu E by kBT is less than 1, or mu E will be less than kBT. So under these conditions, the Langevin function reaches to A by 3. So this result is important. So when the field strength is very high, we are getting it as A by 3. Now from equation 3, we have mu cos theta is mu L of A. So mu cos theta will be equal to mu A by 3. This is under high field strength. So let us substitute now for A. So mu by 3 into A is mu E by kBT. So what we get here is mu into mu is mu square E by 3 kBT. So mu cos theta is mu square E by 3 kBT. This is equation 4. Now from the definition of polarizability or oriental dipolarization, what we have seen, it is the alpha D. We may write it as alpha O. O here represents the orientation, or alpha D, which represents the dipolar. Both represent the same. It is mu upon E. What is mu here? Mu cos theta by E, or mu cos theta is equal to alpha naught into E. So let us now equate the two equations we have. Alpha naught E is equal to mu square by 3 kBT into E. What do you have here? In this equation we had mu square E is equal to mu cos theta is equal to mu square E by 3 kBT. And here we have mu cos theta is equal to alpha naught E. So in 4 also the left hand side is mu cos theta. In 5 also the left hand side is mu cos theta. So we are going to equate the right hand sides. So mu square E by 3 kBT should be equal to alpha naught E. So that is what we are doing here. Equating 4 and 5, we are getting alpha naught E is equal to mu square by 3 kBT into E. Now this E and E gets cancelled. So we can write alpha D or alpha naught. D when we are calling it as dipolar, O when we are calling it as orientational. So is equal to mu square by 3 kBT. So this is the result. I'll take this as capital 3 due to orientational polarization. So what are these terms represent? Mu is representing the dipole moment, Kb is the Boltzmann constant, T is the temperature, and alpha D or alpha O represents the orientational or dipolar polarizability. Now what is the total polarizability? Total polarizability is due to the electronic polarization, ionic and orientation. We also have something called alpha S, which is space charge polarization, and it is negligibly small and we are going to neglect it. This alpha S we are going to neglect the value of alpha S. So when we are simply neglecting the space charge polarization, we have alpha is equal to alpha E plus alpha I plus alpha naught. So what did we get in equation 1? What did we get for alpha E? It is 4 pi epsilon naught R cube. And then in equation 2, we have got alpha I, that is the ionic polarization, which is E square by omega naught square into 1 by capital M plus 1 by small m. This is alpha I, the ionic polarization. And in the third equation, we have got alpha O. So what is alpha O we got? Mu square by 3 kBT. So now the total polarization when we want, so we are going to substitute these values of alpha E, alpha I and alpha naught from these main equations 1, 2 and 3. So when you substitute, what you are getting, alpha is equal to 4 pi epsilon naught r cube. This is the contribution from electronic polarization, plus E square by omega naught square, 1 by capital M plus 1 by small m. This is due to ionic. And then we have mu square by 3 kBt. This is due to orientational. So the total polarizability is given by this equation, which we call it as the Langevin-Debye equation. Sometimes you may be asked to directly derive the Langevin-Debye equation. So then we have to do step by step. What are the contributions to the polarization due to all the four? Derive expressions separately, substitute, and then we get the total polarization or the total polarizability as alpha due to all the four, where we are neglecting this alpha s, that is a space charge polarization. So let us see the diagram, putting it in a nutshell to understand what are the differences. So in electronic, what we have seen, in the absence of the field, the positive and negative charges are coinciding and the net dipole moment is 0. But when a local field is applied, when E is not equal to 0, the positive and the negative ions are getting displaced in the opposite direction. This will be the negative plate and this will be the positive. So this is how the field is. Now then comes the ionic. So in ionic, what is happening? The positive and the negative ions. So how they are separated? This is positive, this is negative. They are like this in the absence of the field. But when the field is applied, they are getting separated. So positive and negative. So here you have negative. This is how they are getting polarized in ionic polarization. Then comes the orientation or dipolar. So in dipolar, we are taking a polar dielectric where there is always dipoles, but these dipoles are oriented in random directions, so the net dipole will be 0, moment will be 0. And when on applying the electric field, what happens? These positive will be oriented in the direction of the field, negative plate, and the negative towards the positive. And then you have interfacial or space charge polarization, so which is very small and we are neglecting the space charge polarization. So for clarification regarding any type of polarization, you can refer to books Introduction to Electrodynamics by David J. Griffiths, and also you can refer to Concepts of Physics by H.C. Verma. So most of the slides that I have prepared are the material taken from these two books, so you can refer to them for any clarification. So thank you and see you again in the next slide.
Like, share and subscribe. Hit the bell icon for more updates.